So when scientists make measurements, they report them in a very particular way. We report all the certain digits and the first uncertain digit. And that tells the reader, how closely do you know this number? Because if I say, 100, well, do you mean that was 100 to the nearest tenth? Or was that 100 to the nearest 10? Don't know, right? Did you use a really precise instrument to measure that? Or was it just kind of an estimate? This is two tables that take up an awful lot of space for what they've got in them, just showing how the measurements are reported differently. So here it's recorded to the nearest tenth of a parts per million, and here it's to the nearest one. So when we look at a scientific measurement, the last digit is going to be uncertain. And sometimes it'll tell you, like it might say 9.9 plus or minus 0.2. It might say that. And then you know that this is the uncertainty in that digit. Most of the time, though, there's nothing there. And so then what we understand, if we're not told otherwise, is that the uncertainty is plus or minus 1 in the last digit. So let's look at this one. So this is plus or minus 0.1. So that tells me that number, the measurement there, the person who's measuring this is saying it's between 7.3 and 7.5. Could be anywhere in there. Okay? Over here, the uncertain digit is the only digit which is in the ones place, and so the uncertainty there is plus or minus 1, which tells me by looking at it that this is between, the smaller one goes first, between 6 and 8. That's a much bigger spread, right? And I can tell that just by looking at the measurement. So that's how scientists report measurements. Thing to realize about measurements is that no measurement can be exact. There's always uncertainty in a measurement. I mean, you can get more and more precise, more and more careful, but there's a limit to how carefully anything can be measured. And so any measurement has uncertainty. So let's look at a couple of practical examples and how do we report these things. So the number of digits that you record when you measure, the mass or something, depends on what you're using to measure it. Depends on the measuring device. And kind of a shorthand is we say, read between the lines. So over here, we're weighing this pistachio on this little kitchen scale. Ignore the ounces. And let's look over here. There are markings that represent 1 gram, right? That one says 0. This one says 10. And so each of these lines in here represents 1 gram. So when we look at the line here, we see it's between 1 and 2 grams. Is there any uncertainty there? Well, I think it's less than 1. No, it isn't. It's bigger than 1, right? Everybody's going to agree on that. It's less than 2. It's literally between those two lines. No uncertainty. So that's the 1. It's 1 gram. It's 1 point something is what we know. 1 and a little bit, right? Oh, how much little bit? Well, that's the estimate part. And it really is just an estimate, almost a guesstimate. So you look at that and you're like, well, it's less than halfway, right? So I think it's less than 1.5. It's definitely more than 1. So there could be multiple correct answers. So in this example, they thought it was 1.2. So we report 1.2 grams. Somebody else might report that as 1.3 grams. That's okay. There's uncertainty in the last digit, but this still has information. 1.2, even if I'm not real sure about the 2, it's like, well, it's clearly smaller than like 1.8 or 1.9, right? It's down towards the bottom of it. So there's information there, even though it's not certain. So what we do is we find out what the individual lines mean. Here the marking is 1 gram. That's the ones place. And then we estimate the next decimal place. So if we've got a ruler where the lines represent 0.1 centimeter, that's the tenths place, we're going to estimate the next decimal place, the hundredths place. We're going to read between the lines. On a thermometer, a glass thermometer's over here, each little line represents 1 degree Celsius. So we'll estimate a tenth. Here's a couple examples. So here's that thermometer. So we got 90 and 100. We can figure out that that's 95, and this must be 91, 92, etc., right? So each line, the lines are 1 gram. So that means I'm going to estimate the next decimal place. That's the ones, so I'm going to estimate 0.1. Okay, what did I do wrong there? Grams. Brain fart. Degrees Celsius. So we're going to estimate the 0.1 degrees. So we're going to look at this red line here. It's kind of behind the 100. I didn't do a very good job taking this picture. 100, 101, 102, 103. So, it looks like it's 103. Could be a little above, a little below. So 103, any reasonable person looking at that would agree is 103. It's the next decimal place where we're going to have differences of opinion. So you might say, well, it looks like it's right on 103. Well, we still need to write something in the tenths place. So we're going to write 103.0 degrees Celsius. Because then the person reading this says, oh, they were estimating over here. If I just report 103, they're going to say, well, they were estimating the 3. They mean it's between 102 and 104. No, that's not at all what we meant. We meant it was between 1.29 and 1.31. That's much smaller, right? So we're going to estimate that next place. If it looks like it's right on the line, you put a 0 there. Otherwise, you do your best guess between the lines. Over here for this one, this is a graduated cylinder. We've got 4 and 5, those are milliliters. And so these lines represent tenths of milliliters. Right? So here the line equals 0.1 milliliter. So then we're going to estimate the next decimal place, which would be 0.01. So this is what's called the meniscus, this curved surface of the liquid. And the glassware is calibrated for you to measure to the bottom of the meniscus. So we're looking at the bottom of this kind of gray shadow. So it's clearly between the 4 and the 5. And this would be 4.5, this line, and that line would be 4.6. So I think we can all agree it's 4.5 something, right? So 4.5, those are the certain digits, and then we're going to read between the lines and estimate the next digit. What do you think? 8? 4.58 milliliters? Somebody might say, no, I think it's 4.57. Okay. We can't be certain. It's okay. But it is information. Any questions? We'll be practicing this in lab. So the precision of our measurements depends on the instrument that's used to make the measurement. But then a lot of times we do calculations with those numbers. And when we do calculations, we want to preserve the degree of precision. We don't want it to suddenly get super precise or super imprecise. We still want it to reflect the actual uncertainty from the data. So how do we keep track of that? Well, we could use calculus to do that. Anybody want to do that? No, not really. Or we can use this kind of shortcut called significant figures. A lot of students hate significant figures, and I don't blame you. If you don't understand how they work, it's just this mystery, right? And you almost feel like you're just guessing, taking a stab in the dark. It doesn't have to be that way. You can actually understand how it works, and then it's easy to remember. It's like playing a game. You learn a new game. We got a new game for Christmas called Azul. It's got these cool little tiles. And, we're going to play the game. Nobody knows how to play the game. Sit down and read the rules. Like, oh my goodness, what are they talking about, right? And you can read through all the rules and you're like, okay, I read the rules, still don't understand. You kind of have to start playing the game and things start happening. And then you're, oh, that's what that meant. Okay. And then after you played the game, you're like, oh, now I understand how it works. Once you learn the game, you don't have to go look at the rules anymore. Once you learn sig figs, you don't have to think about the rules anymore. You just know how to play. So let's all learn to play the sig fig game. So what we mean by significant figures, sometimes called significant digits, these are going to be all of the certain digits in the measurement and the estimated digit. Okay? And if there's any place-holding digits, those are not considered significant figures. But the more sig figs you have, the more precise the measurement is. So here are the rules for counting sig figs. First one, non-zero digits. So any number that is not a zero, you count. So those are bolded here in case you weren't sure which ones were not zeros. So that one's easy. If it's not zero, it counts. If it's zero, then it gets a little more complicated. There's 3 kinds of zeros. So these are interior zeros. So those are zeros that are stuck between non-zero digits. You always count those. Then there's leading zeros. The leading zeros come at the beginning of the number. These numbers are going to be less than 1. It's going to be 0.000 something something. The purpose of those zeros is to locate the decimal point. They're not reflecting measurement. If I measure something and I say, well, that was 2.5 centimeters long. What if I put a couple zeros in front? Well, that looks weird. Do they really mean anything? Do we need them? Do they change anything? No. Why don't we write them up there? We don't need them, right? We don't need those zeros. There's a decimal point, and it's held by non-zero digits. We don't need it. But this number, if we don't write those zeros, 0.23. Well, how many spaces are in there? Well, we need the zeros to tell us. And the zero before the decimal point, its job is just to say, hey, there's a decimal point down here, because otherwise they can get overlooked. So these zeros are just holding the decimal place. They're not reflecting measurement. They're not significant figures. So interior zeros, always significant. Leading zeros, never significant. And then trailing zeros, sometimes yes, sometimes no. So trailing zeros, and the way I explain this is a little different than what the textbook says, but the outcome is the same. So if you like the textbook version, go ahead and use that. This is how I think of it. So trailing zeros, as the name implies, come after the other numbers. So here are 39.0, 120.00. There's 3 trailing zeros there. It's all the zeros that are at the end. If you have a decimal point that's actually written, then you count all the trailing zeros. Doesn't matter if they're before or after the decimal point, you count all of them. because with this decimal point here, that 0 is not needed to locate the decimal point, right? The decimal point is actually written there. We're not guessing around where that is. But then sometimes we have trailing zeros that would come before an implied decimal point, like the number 300. There's no decimal point in it. Where would the decimal point go if we were going to write a decimal point? Well, it would go right there, right? 300, decimal point, and then other stuff. So we know where the decimal point is, where it would be, because of those zeros. If we leave the zeros off, then it becomes 3, which is not the same as 300, right? So those zeros, just like these leading zeros, are holding the decimal place. So technically, these are ambiguous. You can't tell just by looking at them if they're significant or not. This is just a poor way of writing numbers because it doesn't communicate well with the reader. I don't know, in 300, did you measure that? 300 people, was that to the nearest one? Or were you estimating, it looks like there's about 300 people, between 100 and 200. 200 and 400. You know what I mean. One of the things that's really nice about scientific notation, and I'll mention that a little bit more on Thursday. When we put a number into scientific notation, all of the non-significant zeros go away. So let's say I put 300 into scientific notation. So here's a refresher on scientific notation. So for scientific notation, you're going to write the first, that's kind of small, the first non-zero digit, and then the decimal point would go after that, and then any other significant digits. These, though, because, wrong one. These are not significant digits. Well, we're going to assume they're not. We don't really know for sure. So what we're going to do is we're going to assume the worst. So I'm moving the decimal point from where it's implied 2 places. So I've got 3 times 10, and I moved it twice. I said 3, didn't I? I count 1, 2, and say it's 3. Yes. I'm tired. Okay. We move the decimal point 2 places, and that gives us the exponent on 100. And then the big question is, positive exponent or negative exponent? The book talks about moving the decimal point right is one and left is the other, and I can never remember that. So 300, was that a big number or a small number? It was a big number, right? You think about 300 hot dogs, that's a lot of hot dogs, as opposed to a number like this, which is a small number, right? Big number. How do I feel about big paychecks? Positive or negative? Positive, right? So if it's a big number, it's a positive exponent. Let's put this guy in scientific notation. I'll clean up the scribbles I did there. So the first non-zero digit there is a 2. I'm going to put the decimal point after that, and then I'm going to write any of the other significant digits. So I've just got the 2 and the 3, so 2.3. And then I'm going to look, I move the decimal point 1, 2, 3, 4. 4 places. That tells me what the exponent is. So times 10 to the 4. Big number or small number? Small number. How do I feel about small paychecks? Negative. So this is a negative exponent. When you get the sign wrong, you change the value of the number. This is by so much, like thousands or even millions, a factor of a million, right? And so we don't want to get the sign wrong. We don't need any placeholder zeros here. because there's no leading zeros, because the decimal point always comes after the first non-zero digit. So all the leading zeros will go away. We don't need trailing zeros just to hold the decimal point, because the times 10 to the 2 part is holding the decimal. Okay? So when you look at a number in scientific notation, everything before the times sign is significant, whether it's zeros or not. So this one has 2 sig figs, and this one has 1. What if the writer of this meant that it was measured to the nearest thousand? In other words, that this is the digit that was uncertain. We can't tell that from looking at this, but if we write it in scientific notation, then we can communicate that. So 1 point, and these first 2 are certain, and this is the uncertain. We always include the uncertain digit, so I'm going to include the 1.00. So I'm including that uncertain digit times 10 to the something. So the decimal point would be here, 1, 2, 3, 4, 5, times 10 to the 5. Big number, positive feelings, positive exponent. These zeros are in here because I intentionally wrote them. They are not there to hold a place. I don't need them for that because this holds the place. Any questions? So measurements always have uncertainty. There are numbers that have no uncertainty. We call these exact numbers. And so if these numbers come up in calculations, they're not going to limit the number of significant figures in the answer. So we could think of them as having an unlimited or an infinite number of significant figures. And these numbers come about by exact counting of discrete objects. Oh, my 2 pieces of chalk are gone. Here they are. How many pieces of chalk? 2. You sure it's not 2.1? It's 2 pieces, right? 1, 2. Exact counting. It's exactly 2. So if I wanted to write lots of significant figures, I could write 2.0000, and I could go forever. It's exactly 2 things. There's no uncertainty at all. So that's an example, counting of discrete objects. Now, if it's a unit, like 2 feet, not meaning the feet that you're standing on, but the length measurement, you can't count a foot. It's not an object, right? You're using a ruler to measure it. There's going to be uncertainty. These can also come up as integral numbers that are part of an equation. For example, the diameter of a circle equals 2 times the radius. It's exactly 2 times the radius. There's no uncertainty in that. Defined quantities. 1 gallon is defined as 4 quarts. So that's exact. So conversion factors like that one, some of them are exact because they're defined quantities and others are not. So generally, if you're within the same system, there's the English or imperial system and there's the metric system. Gallons and quarts are both volume measurements in the English system, and it's defined that way. But if you go between the metric and the English system and you say, well, 1 kilogram is 2.2 pounds. Well, it's not defined that way. That has to be measured, and so that one's not going to be exact. The one example I want you to be aware of, where it's between English and metric, and it is exact, is that 1 inch is exactly equal to 2.54 centimeters. And that's because they redefined the inch to be exactly 2.54 centimeters. It was really, really close, and they're like, okay, it's exact now. So if you're using this as a conversion factor, it's not going to limit the sig figs in your answer. So let's practice this a little bit. 554 kilometers. How many sig figs? 3. 7 pennies. Can you count pennies? Can you count exactly 7 pennies? So that's going to be one of those exact numbers. Well, it's asking how many. Infinite. You could say it's got an infinite number, an unlimited number of sig figs, or like on the worksheet, it's going to ask you this. You can just write exact. So on the worksheet, there'll be examples like this, and you can write infinity or the word exact. Either one's fine with me. If there's questions in Mastering Chemistry, the computer can be a little pickier about stuff like that. 1.01 times 10 to the 5 meters. 3. Scientific notation, everything before the times sign is significant. So you just count all the digits, there's 3 digits. 0.00099 seconds. 2. So these zeros at the beginning are holding the decimal place. The leading zeros don't count. If we put that number into scientific notation, those zeros go away. How about 1.4500 kilometers?
5.
Yep, that's going to be 5. We have trailing zeros, and there's an actual decimal point, so they all count. Here we've got another number with trailing zeros, 21,000 meters. Is there a decimal point? There's a comma, but there's no decimal point. So it's ambiguous. We're not sure. Well, if we're doing calculations and we need to have a number of sig figs, we can't use ambiguous in our sig fig rules. We're going to assume the worst. So we'd say 2. 2 sig figs there. Any questions? So when we do calculations with data, measurements, we shouldn't gain or lose precision. Okay? We want to preserve that. And sig figs is a very simplistic way of doing that. Differential calculus is the official way to do that, but we decided we didn't want to do that. I did it in college, and then I passed the class and delete. So we've got rules. So multiplication, lots of syllables. Multiplication and division are 2 mathematical functions that are related to each other, right? They're kind of opposites, right? Multiplying and dividing are sort of opposites of each other, and so they can share the same rule. So when you're multiplying or dividing, the answer you get is going to have the same number of sig figs as the factor, one of the numbers that you're multiplying or dividing, that has the fewest number of sig figs. So here we're looking for fewest significant figures. So there will be some problems in the worksheet like this where it's, giving these just random looking calculations and wanting you to give the answer with the correct number of significant figures. The first thing to do is just get your calculator out, pretend you have no idea what sig figs are, and just do the math and write down the answer. Okay? Then go look for sig figs. I'm multiplying, I'm looking for number of sig figs. So I'm going to look at each of these things, each of these factors, and count their sig figs. This one's 4, that one has 5, this one only has 2. Which one is smallest, 4, 5, or 2? 2. Okay, 2 is the smallest, so that's how many sig figs the answer has. So I look at the answer that I wrote out. You're not going to count any leading zeros. I've got the 6 and the 7, that's my 2 digits. I'm done. We'll talk about rounding in a minute. Here's dividing. Again, just do the math, write down what the calculator says. And then look, okay, this one has 5, this one has 3, trailing 0 with a decimal point. So then I need to round this to 3 significant figures. That 0 doesn't count. I've got 6, 2, 6. There's my 3 digits. I'm going to call that 0.626. I recommend always writing down what the calculator said, or at least what the calculator said, at least 2 extra digits more than you're going to need in your final answer. Because sometimes you'll need to take that number and use it in a future calculation. You don't want the rounded number because you can get errors from rounding. Or sometimes you realize, oh dang, that was supposed to be 3. It's supposed to be 3 sig figs. Well, if you've got this written out, you can go add a sig fig. No problem, you don't have to redo the calculation. So adding and subtracting are another pair of operations that go together, right? They're kind of opposites of each other. In adding and subtracting, what we're looking at is the quantity with the fewest decimal places. That's the simplest way to think of it. So here I've got, they don't have the plus sign there, which bothers me. We're adding 2.345 plus 0.07 plus 2.9975. Just do the math, write down what the calculator says. And then here we're looking for decimal places, not number of sig figs. So this one has 3 decimal places, the 3, the 4, and the 5. This one has 2 decimal places, the 0 and the 7. These are not sig figs, these are number of decimal places. And this one has 4 decimal places. So the smallest is 2, my answer should have 2. Now the reason they stack this up is because this can help us to understand what's going on. So I'm going to go in here and I'm going to underline the uncertain digit in these measurements. It's always the last digit. Not hard to pick out. It's just the last one. The last digit is always the uncertain digit. So I think about doing the math here, and I'm adding this 5 to no idea what this is. I just kind of have to assume it's nothing because I don't know any better, but I'm going to get a 5. Am I certain that that's a 5? No way. I wasn't even certain that this was a 5. So I'm going to underline that one because that one's uncertain. Now, this 7, we're certain about. So I'm adding 7 to a 5 that we're a little iffy on, and something we know absolutely nothing about, and I'm getting 12. Am I certain about that 12? Not at all. Scary when that happens. So then you have to carry the 1. So now I'm adding a certain 4 and that 1, an uncertain 7, and a 9. And I'm coming up with 21, thank you. It's like 11's not right. It's 21. We're going to carry the 2. That 21, am I sure it's 21 and not 22? I can't be sure because I wasn't sure about the 7. You see how that works? If one of the numbers we're adding is uncertain, it makes that place in the answer uncertain. So this is also uncertain. Now I've got this 2, a 3 that I'm certain about, I know that that's 0, and a 9 I'm certain about. So when I add these together and get 14, I'm certain about that. There's no uncertainty. And then I carry the 1, and I've got 2 and 2, and I get the 5, and I'm also certain about that one. So in our answer, we want to include all the certain digits and the first uncertain digit. So there is the first uncertain digit. So that was thinking about where the uncertain digits were and the process. An easier way, let's move over to this one. What's this line business? Well, you stack the numbers up like you're going to do it by hand, so the decimal points line up. And then you see, well, which number ends first? And you draw a line to the right of that. Because this is the first uncertain digit. And this guy's going to go on beyond, but this is going to make that digit uncertain. So you draw a line at the end of the number that stops first, and that's going to be where your answer stops. So there's multiple ways of thinking about this. You just need to get clarity on one of them, and use the rule. And so part of the worksheet today is you're going to be trying these in class, right? And you can come up and say, am I doing this right? And I'll say yes, or I'll say no. Let's talk about what's happening here. So, because that's the playing the game, right? You can't learn the game from just the rules. It's too confusing. You have to actually start playing and apply the rules, and then things start to make sense. Rules for rounding. This works in the workplace and in school. You figure out what your boss or your teacher wants, how they want you to do it, and you do it that way, right? And that makes life go easier. There's different ways of rounding numbers. This is the simpler method. You look at the first digit that you're knocking off. Is it 5 or greater? Round up. Less than 5, round down. There's another way where if it's a 5, then you look at the next one, and odd goes up and even goes down, or the other way around, I don't remember. That's too much work. We're not going to mess with that. We're just going to look at the first digit we're losing, 5 or greater, round the previous one up. When we're rounding numbers, it's really, really important that we don't change the magnitude, the overall size of the number. So sometimes we need to round in the tens place, not tenths, but tens or hundreds or thousands. And sometimes people come up with just ridiculous answers. So let's look at this one. We've got this amount, $24,938.99. We're supposed to round to 3 significant figures. So we're going to count digits, 1, 2, 3. So the 9 is going to be the last sig fig, the last significant figure. So 2, 4, 9. Is that right? No. I took 24,000 and rounded it to 200. We need zeros to hold the places for these things that went away. 24,900 is that number rounded to the nearest hundred. But I see this every semester, people round a number like that to 200 when it's 24,000. It's easy to do. So what I encourage you to do is anytime you're rounding over here to the left of the decimal point, put the number in scientific notation and then round it, and this never happens. So if we put this in scientific notation, I've got 2.4938899 times 10 to the something. Let's get rid of that. So again, we're counting how far are we moving the decimal point, and we're taking it from where it actually is. We're not counting from the end or anything. You're just, don't make it harder than it is. Just take it there, and we're moving it over here. So we're going 1, 2, 3, 4 places. It's easy to miscount stuff like that. So yeah, go ahead and take your pencil or your finger and actually run. So 4 places. So this exponent is a 4. Positive or negative 4? Positive. I'd feel really positive if my monthly paycheck was $24,000. It's not. So there I have the number in scientific notation. Now, if I round to 3 significant figures, the 2, the 4, and the 9, and I look at this guy, it's less than 5, so it rounds down, and my answer is 2.49 times 10 to the 4. I don't have to worry about putting in placeholder zeros. I don't have to worry that I change the value. Because, we could take a, used car maybe, and the price is $24,938.99. So, well, let's just, round it a little bit. I'll give you $249 for it. Yeah, not going to work, huh? This is more about the rules for rounding, and the thing I really want to point out here is It's only that first digit that's being dropped that determines where you're going to round. So these were all supposed to be, we're supposed to round them to 2 significant figures, so I'm going to keep the 3, and I'm just going to look at the next digit. I'm not going to start at the end and work my way back. It's a lot of work, and it's wrong. I'm just going to look at the next digit. It's less than 5, so this just stays 5.3. This one, 5.35, I'm keeping the 3. I'm going to look at the next digit. That's 5 or greater, so I round up, and that would be 5.4. When we do multiple step calculations, we don't want to round the individual intermediate answers. It's best if you can just do the entire calculation and write down the answer and then worry about the sig figs. But sometimes you literally had to do it in steps. And this is where recording a couple extra digits on all your numbers will make things easier. We don't want to round the intermediate steps because if we round each step, those roundings can give us an error in the final answer. So we want to avoid that. So we want to carry at least 2 extra digits. And if you're not sure, it's always better to write down too many digits than not enough. Because we can always go back and round it later, but we can't go back and add more digits in without redoing the calculation. So this is an example, and we'll see this examples like this in the worksheet, where we have mixed operations. So we have multiplication that uses one rule, and subtraction uses the other rule. We have to apply the rules separately. So we'll look at the subtraction, do the subtraction, and apply the rule for rounding that to the right number of significant figures. So when we're looking at subtracting, we're looking at decimal places. This has 3 decimal places, that has 2 decimal places. The calculator gives us this answer with 3 decimal places, but we have to be smarter than the calculator and recognize that the second decimal place is uncertain. I don't want to round it there. I'm going to underline it. So when I do the rest of this, I'll look at, that's the last sig fig. Okay. Then I bring these other numbers in and do the multiplication. That's what the calculator tells me. And then I look, well, this one has 3 sig figs. That one has 4 sig figs. This one kind of looks like it has 3, but I underlined that one, telling myself, oh, you need to stop there. This only has 2 significant figures, so I'm going to round this answer to 2 significant figures. So I'm going to keep the 1 and the 9, it rounds to 19. Any questions?